What if everything we thought we knew about the size of the universe was wrong? What if the cosmos is not just vast, but impossibly vast? Late at night, when the world goes quiet, a new eye opened in space. Not to confirm our theories, but to shatter them. A telescope simply discovered something impossible. The universe we thought stretched 14 billion light-years actually spans 93 billion light-years throughout. The James Webb Telescope regarded into a patch of empty sky and observed 800,000 galaxies hiding within the darkness. Galaxies that shaped while the cosmos was most effective 300 million years old. Black holes billions of instances greater massive than they should be. Structures stretching tens of millions of mild years when there wasn't enough time for them to develop. The whole lot we believed approximately the universe's size was wrong. In case you're equipped to peer what is truly available, hit that like button and subscribe. We begin now. Mild left this galaxy 280 million years after the massive bang. It traveled via increasing space for over 13 billion years now. James Webb captured it. The galaxy's call is MOM Z14 and astronomers confirmed its distance in 2025. This single discovery pushed our view of the universe back to a time, whilst the whole lot became nevertheless forming, nonetheless raw, nonetheless impossibly younger. Right here is what makes this insane. The universe is 13.8 billion years old today. Whether Z14 existed whilst handiest 2% of that point had handed. Consider that ratio. If the universe's whole records became 1 year, this galaxy shaped on January 7th. We are searching at cosmic infancy. The invention passed off due to the fact James Webb operates differently than older telescopes. It hunts for something referred to as crimson shift. While mild travels across billions of light years, area itself expands. That expansion stretches the light waves, pulling them from visible colorations into infrared radiation. The farther away something is, the more its mild gets stretched. MOM Z14 has a pink shift cost of 44. That variety way extreme distance. It beat the preceding report holder by just 10 million years, which sounds small, but inside the early universe, the whole lot modified rapid. What shocks scientists is that MOM Z14 isn't always a tiny speck. The galaxy is shiny, its miles actively forming stars throughout a burst of fast creation. Nitrogen tears interior, it reflect historic famous person clusters we see in our own galaxy these days, suggesting that megastar formation labored the identical manner even again then. This must not be viable in line with older fashions. Galaxies have been alleged to grow slowly, carefully over hundreds of tens of millions of years. MOM Z14 indicates us they did no longer. James Webb found it with the aid of combing through current pictures, searching out applicants. Whilst astronomers spotted the faint signal, they grew to become the telescope returned toward it in April 2025 for affirmation. The spectroscopy got here returned clean, confirmed, no longer a concept, now not a guess. Actual statistics proving this galaxy existed at the brink of what we can observe. Right here is the frightening part. MOM Z14 is probably not the restriction. The Nancy Grace Roman Space Telescope launches in 2027. Designed to experiment massive quantities of sky straight away, it'll in all likelihood locate galaxies even farther again. Each new discovery pushes the boundary closer to the large bang itself. And whenever we push that boundary, we discover something that must no longer be there, but something forming too rapid, shining too vivid, current too early. The universe had much less than 300 million years to create MOM Z14. 300 million sounds lengthy, but in cosmic terms, it is a blink. For assessment, Earth has existed for 4.5 billion years. The dinosaurs walked around for 165 million years. MZ14 assembled itself in much less time than that. Stars fashioned, gasoline collapsed, shape emerged, it all going on inside the darkness of the toddler cosmos. What concept we knew about galaxy formation is crumbling. And that is simply the beginning. James Webb does now not see like you see. It cannot discover seen light. Instead, it captures infrared radiation that's invisible to human eyes. This design desire is what makes the telescope so effective for looking on the early universe. Without it, none of these discoveries could exist. When you have a look at a celeb, you spot mild that left it years ago. The celebrity nearest to us past our very own is over 4 mild years away, which means the light you see tonight left that famous person 4 years inside the beyond. You are always looking backward in time when you look up. James Webb takes this precept to an intense. It stares at gadgets so remote that their light has been journeying for over 13 billion years. A telescope is a time device. Infrared vision matters due to growth. The universe is not static. Area grows larger every 20D. As it grows, it stretches everything interior it, which includes mild waves. Mild that started as ultraviolet or visible radiation gets pulled into longer wavelengths. By the time it reaches us, it has shifted absolutely into infrared. Gadgets from the early universe emerge as invisible to telescopes that handiest see visible mild. The Hubble Space Telescope couldn't locate galaxies like Memo Z14 due to the fact their light had redshifted past what Hubble may want to come across. James Webb sits at a region called range 2 to approximately 930,000 mi from Earth. This position maintains it in permanent shadow from each Earth and our famous person. That's important. Infrared sensors must be kept rather bloodless. If they warmth up, they invent their personal infrared glow that drowns out the faint alerts from distant galaxies. Webb's contraptions function at around 370 Df, that is chillier than the floor of Pluto. The telescope's number 1 reflect spans 21 ft across. It's made from 18 hexagonal segments covered with gold. Gold reflects infrared mild higher than some other cloth. Each phase may be adjusted, in my opinion, by tiny motors, permitting the whole replicate to consciousness flawlessly. This precision method net can let from items 100 times fainter than what Hubble out to sea. Here is the way it finds early galaxies. Astronomers' application internet to look at precise patches of sky for hours or even days. The longer the telescope stares, the greater faint mild it gathers. Photons that left galaxies billions of years ago trickle in one at a time. Net's detectors rely them. Through the years, and picture builds. Galaxies that could be invisible with a shorter statement turn out to be seen with staying power. The spectrograph devices then analyze the light. They split it into person wavelengths, creating what scientists name a spectrum. Each element emits mild at specific wavelengths, growing a unique fingerprint. Hydrogen seems distinct from helium. Oxygen appears one of a kind from carbon. By means of reading those fingerprints, Internet determines what a galaxy is fabricated from, how fast it is moving, and most importantly, how a long way away it's far. The purple shift dimension comes from these spectra. It is the important thing to unlocking cosmic distance. What makes this terrifying is the size. Each deep area photo net takes reveals lots of galaxies, and each one is a international we will never visit. An area to this point away that we are seeing it, because it become whilst the universe changed into a baby. Close your eyes and image nothingness. That's what the universe appeared like for its first few 100 million years. Darkness anywhere. No stars but, no galaxies, simply hydrogen and helium fuel floating inside the void, slowly clumping together underneath gravity's pull. This era is referred to as the cosmic darkish a long time, and it lasted longer than you would suppose. Then something modified. Gravity won. The fuel collapsed into dense wallet. Strain built, temperatures rose, and the primary stars ignited. That moment ended the dark a while and commenced the cosmic dawn. LS 14 formed during this sunrise when mild was simply beginning to flood the universe. 280 million years sounds like a long term. It is not. Now not for constructing a galaxy. Consider the stairs required. You need gas clouds to fall apart. You need stars to form from that fuel. You want those stars to cluster collectively. You need heavy factors to get created internal the one stars, which takes more than one stellar generations. Every step calls for time. But Mao Z14 finished all of this in underneath 300 million years. Right here is what the universe gave the impression of lower back then. Area was smaller, tons smaller. Everything changed into closer together. The common temperature turned into better, due to the fact all that count number was compressed into less quantity. Radiation from the Big Bang nevertheless stuffed the cosmos, though it had cooled notably. Dark B-counted halos have been forming, creating gravitational wells wherein ordinary rely ought to gather. These halos acted like invisible scaffolding for the primary galaxies. The fuel itself became almost natural hydrogen and helium. No oxygen but no carbon, no nitrogen, not one of the factors that make up planets or existence. Those elements had to be forged inside stars first. While big stars exploded as supernovas, they scattered heavier elements into space. The following era of stars incorporated the one's factors. This technique is referred to as stellar nucleosynthesis, and it takes time. A couple of cycles, multiple explosions. What confuses scientists is that MOMZ-14 already shows signs and symptoms of nitrogen, meaning as a minimum 1 or 2 generations of stars had already lived and died interior this galaxy. In less than 300 million years, stars fashioned, burned through their fuel, exploded, enriched the fuel around them, and allowed new stars to form with those enriched materials. The timeline is compressed nearly impossibly tight. Examine this to our own galaxy. The Milky Way has existed for over 13 billion years. It has had time to undergo countless cycles of famous person birth and death. It has had time to accumulate a rich inventory of heavy factors. Earth itself contains iron, silicon, gold, uranium, and dozens of different elements that did now not exist when the universe was young. All of that fabric got here from ancient supernovas. MZ-14 started out that equal manner in a fragment of the time. And it is not alone. James Webb has observed over 100 galaxies from this same early duration. Each one brilliant, each one actively forming stars. Every one challenging the models that expected galaxies must shape slowly. The cosmic sunrise turned into not gradual. It turned into an explosion of hobby. Galaxies appeared rapid, shining intensely, reworking the universe from darkness into light inside some 100 million years. And we are handiest now seeing the evidence 13 billion years later due to the fact lengthy to attain us. What this tells us is unsettling. The universe does now not comply with the gradual, careful development we expected. It actions rapid when it desires to, and the forces using galaxy formation within the early universe had been more potent than whatever we see today. There may be a black hole internal galaxy CANUSA RDZ86. The galaxy existed 570 million years after the Big Bang. That alone is marvelous. What makes it not possible is the black hole's size. It's far extraordinary massive, tens of millions of times heavier than our celebrity, and it's far feeding hastily, pulling independent at a rate that breaks theoretical limits. Black holes shape whilst large stars fall apart. A star 20 times heavier than ours can explode as a supernova, and its core implodes into a black hole weighing perhaps 50 instances what our star weighs. That may be a stellar mass black hole. It is tiny as compared to terrific large black holes which weigh millions or billions of instances greater. How do you get from 50 to a million? You need time, masses of time. The black hole has to consume, it has to eat gasoline dust and different stars over hundreds of thousands and thousands or billions of years. Here is AN United States of America RDZ86 did not have that time. The universe changed into slightly 500 million years old while this galaxy existed. This is nowhere close to enough time for a fantastic large black hole to grow through ordinary feeding. But there it's far showed by spectroscopy from James Internet. No longer a principle, no longer hypothesis, actual facts. The galaxy belongs to a category referred to as little purple dots. Those objects are small, faint, and extraordinarily pink due to their distance. James Webb has observed dozens of them because operations commenced. Most confuse astronomers due to the fact they're either too dense with stars or they include black holes too big for his or her size. CANUS RDZ86 falls into the second one class. The black hole outweighs the galaxy's staria a full-size margin. How did it get that huge, that speedy? There are important theories. First, the black hole ought to have formed from a big fuel cloud that collapsed at once without forming a celebrity first. This would create what scientists call a heavy seed black hole, maybe heaps of instances heavier than our celebrity right from birth. That offers it a head begin. The second principle entails notable huge stars. These hypothetical stars could be hundreds of thousands of times heavier than normal stars. After they collapsed, they would leave behind heavy black holes without delay. Both theories have problems. Direct fall apart requires very precise conditions that may not have been commonplace within the early universe. Notable huge stars are theoretical and feature never been determined. Yet, something created those black holes due to the fact we are able to see them now. The feeding charge makes it worse. James Webb detected gas swirling around the black hollow at terrific speeds. The fuel is rather ionized. That means radiation from the black hollow has stripped electrons from atoms. This is a signature of speedy accretion. The black hollow is consuming count greater than 40 instances quicker than the theoretical Eddington limit. That is the most charge a black hollow should be able to feed before radiation strain pushes away incoming matter. Think about that. Physics says there may be a pace restrict to how rapid black holes can consume. This one is ignoring the limit. It's far gorging itself, growing at a breakneck tempo that must not be viable. If it maintains feeding at this price, it becomes a monster in extraordinarily little time. What scares scientists is the implication. If CAN United States RDZ86 is not particular, if there are lots or tens of millions of galaxies adore it in the early universe, then supermassive black holes need to have formed faster and more without difficulty than we ever imagined. They did no longer take billions of years to develop. They regarded early, hungry, and prepared to eat the whole lot around them. The universe became wild in its young people, violent, speedy, and each rule we notion ruled black hole increase is being rewritten as James Webb continues staring into the past. James Webb began finding them right away, tiny pink smudges scattered across deep subject snapshots. At first, astronomers notioned they had been simply distant normal galaxies. Then the spectroscopy got here back. These objects are not everyday, no longer even close. They're compact, extraordinarily luminous, and their properties make no experience. According to standard fashions, scientists call them little crimson dots, and they may be rewriting the rules of early galaxy evolution. Over 100 of those objects had been diagnosed up to now, all of them percentage common trends. First, they're small, lots smaller than regular galaxies from the identical era. Second, they're pink because their mild has been stretched by means of cosmic expansion. Third, they're brilliant, man or too brilliant for his or her size. And fourth, they include either extremely dense big-name clusters or massive black holes that have to no longer fit in them. Here is what makes them weird. In case you calculate the mass of stars needed to produce their brightness, you get a number this is impossibly dense. The celebrities would be packed so tightly that they might collide and merge constantly. That doesn't appear in any galaxy we see today. Instead, if a top-notch large black hole is producing the mild, then the black hollow is simply too massive for the galaxy web hosting it. In cutting-edge galaxies, black holes weigh approximately 0.1% of the galaxy's total mass. In little pink dots, a black hole can weigh as a whole lot as the complete galaxy's stars combined. Both options ruin the fashions. Astronomers thought galaxies and their critical black holes grew collectively, retaining a balanced ratio. The galaxy paperwork first, constructing up stars over the years. The black hollow grows slower, feeding on gas that falls towards the center. Finally, they reach equilibrium. Little crimson dots display this dating inverted. The black hollow were given big first, overpowering the galaxy around it. Some other mystery is their abundance. Before James Webb, astronomers expected to discover maybe a handful of uncommon galaxies inside the early universe. Instead, there are loads. They may be no longer uncommon oddities. They are commonplace. Which means something system created them become not a fluke. It changed into a trendy part of how the early universe labored. Some scientists think little pink dots are transition gadgets. They might be catching galaxies in the center of a growth spurt, while the critical black hollow is feeding hastily, but the surrounding galaxy has not stuck up. But over the years, the galaxy might develop greater stars and end up a normal quasar, the bright items powered by excellent large black holes that we see at some point of the universe. If that is genuine, then little pink dots are an image of youth, a phase all galaxies undergo earlier than maturing. Others assume they represent a very special formation pathway. Maybe some galaxies shape black holes first and build stars round them later. Maybe dark conk performs a larger function than we found out. Perhaps the early universe had situations that allowed black holes to grow faster than they can these days. One component is sure: little red dots aren't going away. Every new James Internet commentary reveals extra of them. They seem at more than one distances. That means they existed in the course of the primary billion years of the universe. They had been no longer limited to one specific term. They had been anywhere. The most unsettling element is what they are saying approximately are models. We constructed equations to describe how galaxies shape. We ran PC simulations to check those equations. The simulations expected sluggish, constant increase. They anticipated galaxies forming stars over billions of years. They expected black holes staying small relative to their host galaxies. Little pink dots smash all three predictions. The universe became not patient in its youth. It changed into chaotic and fast and severe. Little red dots are the proof, scattered across the sky like cosmic mysteries waiting to be solved. Physics has limits. There are policies about how speedy black holes can devour depend. Those guidelines aren't pointers. They may be outcomes of radiation strain and gravitational forces. A black hollow named LID 568 is ignoring the one's rules absolutely, and astronomers don't have any idea how. The black hollow sits at the center of a dwarf galaxy, seen because it existed 1.5 billion years after the huge bang. James Webb and the Chandra X-ray Observatory each discovered it. The facts came back clean. LID 568 is feeding at over 40 times the Eddington restriction. That restriction is the theoretical maximum charge at which a black hollow can pull and count before its own radiation pushes that be counted away. Here is how the restriction works. While Runaway falls in the direction of a black hollow, it paperwork a swirling disk around the occasion horizon. Friction in this disk heats the matter to hundreds of thousands of degrees. Hot count number emits radiation, consisting of excessive X-rays. That radiation exerts stress outward. If an excessive amount of remember falls in too speedy, the radiation pressure turns into sturdy sufficient to blow away the incoming cloth. The black hole basically chokes itself, preventing faster feeding. This creates a Hubble speed restrict. LID 568 is exceeding that using 40 times 40. Now not 10% quicker, not 2 times as fast, 40 times. That is like announcing a car with a top speed of 100 mph is by hook or by crook traveling at 4,000 mph. The physics have to not allow it. One opportunity is awesome Eddington accretion. This happens while count number falls in from all directions concurrently, overwhelming the radiation pressure through sheer extent. Consider seeking to forestall a tidal wave with a fan. The wave wins. If sufficient gas collapses onto the black hole immediately, the radiation cannot push all of it away speedy enough. The black hollow gorges itself in a brief, severe burst. Those feeding frenzies are in all likelihood uncommon and brief-lived. A black hollow cannot sustain outstanding Eddington accretion for hundreds of thousands of years. The encompassing gas supply might run out. What makes LID 568 important is that astronomers stuck it throughout this short section. It's miles a photo of speedy growth, the type of event that might provide an explanation for how notable huge black holes got so massive so rapid in the early universe. The black hole's mass is distinctly small for extraordinary big black hole, just a few million times heavier than our superstar. That makes experience given how younger the universe was whilst LID 568 shaped. What does not make sense is how vibrant its miles. The power pouring out of the accretion disk is enormous. X-rays scream into space. The encompassing gasoline glows with warmth. If this feeding rate endured for only some million years, the black hole would double in size. Scientists assume events like this might have been commonplace within the early universe. Gasoline was denser back then. Galaxies were still forming, their shape chaotic and risky. Big fuel clouds could crumble immediately onto young black holes, triggering wonderful Eddington feeding episodes. Each burst could add great mass quickly. Over time, via a couple of episodes, a black hollow could develop from stellar mass to great large in a ways much less time than ordinary accretion would permit. James Webb's discovery of lid 568 is essential because it presents evidence for this concept. Before this, amazing Eddington accretion changed into hypothetical. Now we've observed it. We've measured it. We are aware of it takes place. The query shifts from whether it's miles feasible to how often it passed off. The universe is stranger than the equations advocate. Black holes do no longer always follow the bounds we calculate. Under the right conditions, they damage the policies, and within the early cosmos, the one's right conditions may additionally had been anywhere. Believe maintaining a grain of sand at Palms period and looking at the sky. The place that grain blocks consists of nearly 800,000 galaxies. That's what the Cosmos Webb survey discovered after James Webb spent over 200 hours gazing one patch of space. The survey protected 0.6 square of sky. For reference, the total moon covers approximately 0. So, we are talking approximately a place roughly 3 instances the scale of the total moon. In cosmic phrases, this is microscopic, a tiny sliver. But within that sliver, James Webb determined more galaxies than the majority can realize. 800,000 galaxies, every one containing billions or trillions of stars, each one existing at distinctive distances, meaning different times in the universe's records. A few are nearby, displaying us galaxies as they look fantastically currently. Others are so distant their light left them over 13 billion years ago. The survey basically created a timeline of cosmic history, all visible in a single photograph. The Cosmos Webb Challenge used James Webb's near-infrared camera and mid-infrared instrument to capture the information. Astronomers chose the Cosmos field especially as it has very few foreground stars or gas clouds blocking the view. This offers a clear line of sight deep into area. The field has been observed by way of a couple of telescopes over time, together with Hubble, but James Webb's infrared sensitivity allowed it to peer galaxies. Hubble ignored absolutely. What makes this survey revolutionary is its aggregate of width and intensity. Many deep subject images consciousness on extremely small areas, maximizing the observation time to peer the faintest items possible. Cosmos Webb sacrificed some depth to cowl a bigger vicinity, revealing how galaxies are dispensed throughout area. The result is a map displaying galactic systems, clusters, and voids spanning billions of light years. The picture indicates galaxies at each degree of evolution. Spiral galaxies with stylish palms. Elliptical galaxies which can be smooth and featureless. Abnormal galaxies twisted via gravitational interactions. Galaxies within the process of merging, their systems distorted as they collide, and everywhere little crimson dots from the early universe, scattered like embers from the cosmic sunrise. One unexpected finding is the sheer quantity of early galaxies. Earlier than James Webb, fashions anticipated far fewer vibrant galaxies inside the first billion years after the massive bang. The Cosmos Internet survey discovered 10 times extra than predicted. This shows galaxy formation turned into more green and came about faster than theories anticipated. The early universe changed into no longer empty and quiet. It became crowded and lively. The survey also discovered systems forming earlier than anticipated. Galaxy companies and clusters that need to have taken longer to assemble are already seen within the early universe. Gravity pulled galaxies together faster than fashions suggested. The cosmic internet, the massive scale shape of the universe with its filaments and voids, changed into already taking form, while the universe was just a few billion years antique. Each galaxy inside the picture has a tail, every one shaped through a unique aggregate of dark relay, gasoline collapse, and megastar formation. A few experienced violent mergers, some grew quietly over billions of years. Some are actively forming stars proper now, their light displaying the glow of young, warm, stellar populations. Others are antique and dead, their stars lengthy seeing that burned out. They light a ghostly echo of past interest. The Cosmos Internet Survey will be studied for years. Astronomers will examine individual galaxies, degree their distances, have a look at their compositions, and track how they trade over time. Each new analysis will refine our knowledge of cosmic evolution. Every discovery will upload some other piece to the puzzle of how the universe grew from the Bildungsfireball into the based cosmos we see nowadays. And this is simply one patch of sky. There are over 40,000 square ranges across the entire celestial sphere. If each patch contains this many galaxies, the overall range inside the observable universe exceeds 2 trillion. That number is so large it loses, which means we cannot visualize 2 trillion. We can only understand it as a symbol of the universe's incomprehensible vastness. A black hole is shifting through area at 2 million EMF. It isn't always orbiting something. It is not falling closer to something. It is running, fleeing, and it's far dragging a trail of newborn stars in the back of it, like a cosmic scar 200,000 light-year lengthy. The black hollow weighs 10 million instances what our superstar weighs. That is outstanding big with the aid of any degree. Yet, something kicked it out of its home galaxy with sufficient pressure to ship it rocketing through space at 3,000 instances the rate of sound. James Webb confirmed this discovery in 2025, and astronomers are calling it the primary established runaway tremendous big black hole. The object sits in the cosmic all-galaxy gadget. That's simply a couple of galaxies within the system of merging. When galaxies collide, their significant black holes sooner or later sink toward the merged galaxy's center. Typically, in uncommon cases, gravitational interactions can eject one of the black holes absolutely. That's what befell here. There are ways to kick out a black hole this large. First, while two high-quality large black holes merge, they release gravitational waves. Those waves bring momentum, and if they are emitted asymmetrically, they are able to give the resulting merged black hollow effective kick. Consider it like flinch from a gun. The black hole receives pushed in a single direction at excessive velocity. Velocities can attain hundreds of miles, more than enough to get away the galaxy's gravity. The second technique entails 3 black holes. If a galaxy already had a binary pair of black holes at its center, and a third black hollow enter the device for the duration of a merger, the interplay will become unstable. One of the 3 gets slingshot out. That is a 3-body problem, the type of chaotic gravitational dance that has no stable solution. One black hollow usually loses and receives ejected. James Webb determined the black hole by way of detecting a bow surprise in the front of it. As the black hollow flows via intergalactic gasoline at extremely good velocity, it compresses the gas in advance of it, developing a shock wave like a ship moving through water. That taken aback fuel heats up and glows. The telescope also detected the path in the black hole, a long filament wherein gas is collapsing and forming stars. The black hole's passage triggered star formation along its entire route. This is unheard of. Stars forming in the wake of a runaway black hollow. The gasoline gets compressed with the aid of the black hole's gravity as it passes, and that compression causes crumble. New stars ignite at the back of the fleeing massive. The path is visible due to the fact younger stars are brilliant. They shine in ultraviolet and seen light, and their mild receives redshifted into infrared by the point it reaches us. The rate is mind-boggling 2 million EMF. In 120, this black hollow travels over 500 mem. It crosses the space from Earth to our moon in less than 2 mins. At this price, it will break out the cosmic all-machine entirely and wander via intergalactic area as a rogue object. Galaxies without central black holes are uncommon. However, this one is ready to end up homeless. What does this suggest for our information of black hole evolution? Runaway black holes were predicted by means of simulations. However, finding one confirms they exist. It also increases questions about how commonplace they may be. If galaxy mergers frequently eject black holes, there could be lots of rogues drifting via area, invisible, because they may be now not feeding on matter. The invention additionally suggests black hollow mergers in the early universe may additionally were chaotic. As galaxies fashioned and collided at some point of the cosmic sunrise, their black holes would have interacted violently. Some merged, some got ejected. The technique became messy, unpredictable, and ended in black holes scattered across the cosmos. James Webb's potential to discover this object suggests how sensitive the telescope is to faint structures. The bow-shock and megastar path aren't vibrant. They required lengthy publicity times and cautious evaluation to identify. But they revealed something nobody had visible before. An outstanding large black hole in full retreat, racing away from domestic and leaving a trail of advent in its wake. Black holes are colliding intergalaxy device Z7. The device existed 740 million years after the Big Bang. Both black holes are notable big, every weighing millions of times what our big name weighs. They're circling, each different, spiraling inward, and they will finally merge into one even larger black hole. When that occurs, the collision will shake space-time itself. James Webb detected the merger by means of reading the spectrum of light from ZS7. The statistics showed two awesome assets of energetic radiation very near together. Both sources displayed the signatures of accreting black holes, fast-moving gas, extreme ionization, and broad emission traces from atoms swirling at excellent velocities. The two assets are separated via only some 1,000 light-year, and they may be moving closer to every different. That is the most remote black hollow merger ever detected. It is also the earliest in cosmic time. Preceding mergers have been located inside the contemporary universe, but never this some distance returned. The discovery confirms that black holes have been already colliding and merging, while the universe become much less than 1,000 million years vintage. This has main implications for how superb huge black holes grew so massive so quickly. Merges are one of the fastest ways to build massive black holes. In preference to slowly accreting fuel over tens of millions of years, two black holes can integrate their mass in a single occasion. If mergers have been commonplace in the early universe, they may provide an explanation for how terrific massive black holes reached billions of solar hundreds in the first billion years after the Big Bang. The merger system itself is charming. As two black holes orbit every different, they emit gravitational waves. Those are ripples in spacetime predicted by way of Einstein's well-known relativity. The waves deliver energy far away from the gadget, causing the orbits to decay. The black holes spiral closer and nearer, moving faster and faster till they collide. The final merger happens in a fragment of a second, releasing extra power than all the stars within the visible universe combined. We cannot locate the gravitational waves from ZS7 with modern era. The waves are too faint after journeying over 13 billion mild years. However, Destiny observatories may be able to. The Laser Interferometer Area antenna scheduled to release in the 2030s is designed specifically to locate gravitational waves from extremely good large black hollow merges. While it becomes operational, it's going to study activities like ZS7 automatically. What makes this discovery critical is that it affords a preview of what LISA will discover. Before James Webb determined mergers inside the early universe, scientists' idea activities like ZS7 could be uncommon. Now they know mergers had been commonplace, which means LISA will come across a long way greater gravitational wave occasions than to start with expected. The charge of black hollow merges in the toddler universe became a whole lot better than models recommended. The merger also tells us about galaxy evolution. ZS7 is shaped from two galaxies colliding and mixing. Because the galaxies merge, their black holes sink closer to the middle of the brand new combined galaxy. This method is referred to as dynamical friction. The black holes have interaction with stars and fuel, dropping strength and spiraling inward. Subsequently, they form a binary pair which then merges. This series takes place in the course of cosmic records. galaxies collide continuously. The Milky Manor is presently on a collision direction with the Andromeda Galaxy, and they may merge in about 4 billion years. When they do, their significant black holes will in the end merge as well. The method we see in ZS7 is the equal manner, so that it will appear to our very own galaxy within the distant future. The gravitational waves from the ZS7 merger have been emitted 13 billion years ago. They were journeying through area ever on account that, stretching as the universe accelerated. By the point LUSA detects them, they'll have been converted into long wavelength alerts that require area-based totally detectors to look at. Those waves carry information about the masses of the black holes, their spins, and the dynamics of the merger. Destiny astronomers will decode that information to learn information James Internet cannot see. There may be a galaxy named JADES GS140. It existed 290 million years after the Large Bang. James Webb measured its brightness and determined its miles-forming stars at an absurd fee. The galaxy is creating new stellar mass 100 instances faster than models predicted feasible for its age. Famous person formation requires gas. Hydrogen clouds collapse beneath gravity, compressing till temperatures reach 10 million. At that factor, nuclear fusion ignites. Hydrogen atoms fuse into helium, freeing power. A star is born. The procedure takes tens of millions of years from begin to complete, and it calls for precise conditions. The gas ought to be dense sufficient. It ought to be cool sufficient. Turbulence have to no longer disrupt the disintegrate. Inside the modern universe, galaxies shape stars highly slowly. The Milky Way creates approximately 3 new stars in step with 12 months. That sounds rapid, but our galaxy includes loads of billions of existing stars. The megastar formation charge is low compared to the whole stellar mass. That is traditional for mature galaxies. Maximum in their fuel has already been converted into stars or expelled with the aid of stellar winds and supernovas. JADES GS4 is unique. It is forming stars at a charge that could create the mass equivalent of loads or thousands of stars consistent with year. For a galaxy that younger and small, that price is intense. It manner the complete galaxy is a star-forming furnace with gas clouds collapsing simultaneously across its entire quantity. Why is this occurring? One idea involves cold streams of gas falling onto the galaxy from surrounding area. In the early universe, gas turned into dispersed in another way than today. Dark matter halos acted as gravitational wells, pulling in gas from extensive distances. That gas flowed along filaments, streaming into younger galaxies like rivers feeding a lake. The influx provided a consistent deliver of uncooked cloth for megastar formation. Every other opportunity is that the galaxy lately experienced a merger. Whilst 2 galaxies collide, their fuel clouds break collectively, triggering large bursts of famous person formation. The collision compresses the gasoline, causing full-size crumble. Big name formation quotes can spike via elements of 10 or greater at some point of those activities. JADES GZ140 is probably caught within the center of any such burst. The brightness is another mystery. Younger stars are warm and luminous. They emit remarkable amounts of ultraviolet mild. That mild heat surrounding fuel causing it to glow. The combination makes the galaxy shine brightly. But JADES GZ140 is brighter than expected, even accounting for its superstar formation chart. The light output indicates both the celebs are surprisingly massive, or there may be some other power supply contributing to the glow. Some astronomers assume wonderful massive stars might be concerned. These hypothetical gadgets would weigh loads of times greater than common stars. They might burn particularly hot and bright, residing only a few million years earlier than exploding. If JADES GZ140 formed a populace of fantastic large stars, their combined mild could explain the immoderate brightness. However, incredible huge stars remain theoretical. No confirmed observations exist. The galaxy's spectrum indicates sturdy emission lines from oxygen and hydrogen. This confirms active star formation. The lines are broader than expected, suggesting the gas is turbulent and moving at excessive speeds. This turbulence is probably driven with the aid of stellar winds and supernova explosions. Younger, big stars die quick and violently, injecting energy into their environment. That energy stirs up the gasoline, developing chaotic motion. What bothers scientists is the quick time scale. At 290 million years after the Big Bang, the universe barely had time to form the first technology of stars, not to mention build a big famous person-forming galaxy. JADSGS Z140 have to be in its infancy, simply beginning to collect. Instead, it's far absolutely active, generating stars at a breakneck tempo. This suggests galaxy formation was more efficient inside the early universe than contemporary models are expecting. Fuel collapsed faster. Stars fashioned quicker. Feedback mechanisms that sluggish big-name formation in cutting-edge galaxies have been weaker or absent. The early cosmos become a greater efficient environment for building galaxies. Each discovery like JS140 forces astronomers to revise their models. The numbers get adjusted, the timelines get compressed, and the photo of the early universe becomes more chaotic, extra violent, and greater amazing than we ever imagined. The universe is expanding. We've known this since the 1920s. What we do now not recognize is exactly how fast it's miles expanding. Two exceptional methods give two one-of-kind answers, and the discrepancy is huge sufficient that it cannot be neglected. Astronomers call this a Hubble tension, and James Webb just confirmed it's far real. The enlargement charge is measured via various known as the Hubble steady. It tells us how speedy galaxies are shifting far away from us at a given distance. If the Hubble constant is 70, meaning a galaxy 1 megapark away is receding at 70 km, a galaxy 2 megaparsecs away is receding at 140 km. The farther away something is, the faster it movements away. There are most important methods to degree this steady. The primary makes use of observations of the cosmic microwave heritage, the faint glow left over from the Large Bang. This radiation fills the whole universe and carries statistics approximately the cosmos because it existed 380,000 years after the massive bang. Via analyzing tiny temperature versions on this radiation, scientists can calculate how rapid the universe became increasing lower back then. They then use fashions to challenge ahead to the present day. This approach offers a Hubble steady of approximately 67. The second one method uses close-by stars and galaxies. Astronomers degree the gap to galaxies, called Cepheid variable stars and sort supernovas. Both are well understood and may be used as distance markers. With the aid of measuring how fast the galaxies are transferring away from us and evaluating that to their distance, scientists calculate the Hubble regular immediately. This approach gives a value of approximately 73. 6 points is a massive distinction. It is not a rounding error. It isn't always measurement uncertainty. Each methods are particular and had been checked again and again. The discrepancy is actual, and it has endured for over a decade. That is the Hubble anxiety. James Webb's role in this mystery is important. One subject was that Hubble Area Telescope measurements may have errors. Maybe the distances have been incorrect. Perhaps something about how Hubble located Cepheid stars introduced a systematic bias. James Webb can observe the equal stars with higher sensitivity and determination. If Hubble's measurements had been fallacious, Webb could locate special values. Webb did now not discover exceptional values. It showed Hubble's measurements. The distances are accurate. The growth price is truly about 73 while measured the use of close-by objects. The tension due to observational blunders. It's miles real. This leaves two opportunities. Either our model of the universe is incomplete, or something changed in how the universe expands over the years. The usual model of cosmology assumes the growth rate follows a smooth, predictable pattern determined by using the amounts of Rayleigh, darkish count number, and dark strength in the universe. If those assumptions are incorrect, the version breaks down. One idea is that dark electricity behaves otherwise than we think. Dark energy is the mysterious force causing the universe's enlargement to boost up. It makes up about 68% of the universe's total power. We do not realize what its miles, most effective that it exists. If darkish electricity modified over cosmic records, That would provide an explanation for the tension. The early universe might have accelerated at one phi whilst the modern-day universe expands at a distinctive price. Any other possibility is that there's an unknown element to the universe we've not detected but a few new shape of power or rely that impacts expansion. This would be a main discovery equivalent to finding a lacking aspect inside the recipe for the cosmos. Or perhaps the hassle is with the cosmic microwave historical past analysis, possibly the fashions used to interpret that statistics are unsuitable. If the early universe turned into special than we assume, the projections to the modern day might be wrong. The Hubble tension is one of the most important puzzles in contemporary cosmology. It suggests our know-how of the universe is incomplete. Something is missing. Something we've got no longer accounted for. And until we figure out what that something is, the anxiety will stay. A crack in the foundation of our cosmic fashions. There's a galaxy called IP1b. James Webb determined it as part of a survey looking for unusual gadgets in the early universe. The spectrum came again unusual. No oxygen, no carbon, nearly nothing besides hydrogen and helium. This is probably the signature of Populus, 3 stars. The first actual stars to ever form. Stars are divided into populations primarily based on their steel content material. In astronomy, metals imply anything heavier than helium. Iron is a steel. Carbon is a steel. Oxygen is a steel. Modern stars comprise a few cent metals by mass. Those are known as population 1 stars. Older stars include less metallic, perhaps 1/1000%. These are Populus 2 stars. Populus 3 stars might have 0 metals formed from the natural hydrogen and helium that existed proper after the massive bang. No one has ever showed a population 3 megastar. They need to have existed, but they died billions of years in the past. These stars were huge, burning through their gas in only some million years before exploding as supernovas. The one's explosion scattered the primary heavy elements into area, seeding the universe with substances for the subsequent technology. Each big name we see today, along with our personal, carries metals solid with the aid of Populus 3 stars. Locating them is difficult because they are so vintage. Any population, 3 stars nevertheless shining might be within the maximum distant galaxies, seen only as they existed within the early universe. Their mild could be faint and redshifted. Even James Webb struggles to come across individual stars at such distances. As a substitute, astronomers look for galaxies where population 3 stars may nonetheless dominate the stellar populace. LAP1b is a candidate. The galaxy's spectrum indicates nearly no metal traces. The mild is dominated by using hydrogen and helium emission. This can imply the galaxy includes on the whole Populus 3 stars, even though different motives are viable. The galaxy may just have very pristine gasoline that has not been enriched by supernovas yet. Or the spectrum might be displaying gasoline clouds instead of stars. Confirming population 3 stars calls for deeper observations. James Webb desires to appearance longer, collecting extra photons to locate fainter spectral features. If oxygen is absolutely absent, that could make stronger the case. Population 3 stars do now not produce plenty oxygen due to the fact they explode before forming it. Later, stellar generations create oxygen through fusion in their cores and release it after they explode. Why does this matter? Populus 3 stars formed the universe. They were the primary resources of mild after the cosmic darkish ages. Their ultraviolet radiation ionized the encircling hydrogen, transforming impartial gas into plasma. This procedure is known as reionization, and it essentially changed the universe's shape. Without Populus 3 stars, reionization could not have passed off and the universe would appearance absolutely extraordinary. These stars additionally set the degree for all destiny's celebrity formation. Through creating the primary heavy factors, they made planets feasible. Carbon, oxygen, silicon, iron. All of the materials that make up Earth came from supernovas of massive stars. Populus 3 stars started out that procedure. They had been the cosmic alchemists, turning easy hydrogen and helium into the complex periodic table we rely on. Their masses are debated. A few fashions advocate they have been hundreds of instances heavier than our celebrity. Others assume they ranged from 10 to 100 times heavier. The distinction subjects because it affects how they exploded and what factors they produced. Very huge stars may have collapsed at once into black holes without exploding in any respect. If that occurred, they would now not have enriched the universe with metals, delaying the formation of later stellar generations. James Webb's discovery of LAP1b gives a glimpse of what the earliest stars would possibly have gave the impression of. Although this galaxy seems now not to incorporate populous 3 stars, it indicates that James Webb can come across items pristine sufficient to be applicants. The telescope will preserve surveying the early universe, and eventually astronomers will locate definitive evidence of those historic giants. Whilst that takes place, it will entire the story of stellar evolution. We will have discovered stars from every technology, from the primary technology to the modern one. We are able to recognize how stars modified the universe from an easy cloud of hydrogen and helium to the rich, complicated cosmos we inhabit these days. James Webb continues finding huge galaxies inside the first billion years after the Big Bang. Those aren't small dwarf galaxies simply forming their first stars. They're big, nicely developed structures containing billions of stars. They should not exist, but the universe did now not have sufficient time to build them. Galaxy formation is meant to be a gradual manner. Dark counted halos form first, growing gravitational wells. Gas falls into those wells, amassing over tens or masses of hundreds of thousands of years. Subsequently, enough gas collects to start forming stars. The galaxy grows slowly, adding extra mass over the years through non-stop big-name formation, and merges with smaller galaxies. Accomplishing a mass equal to tens of billions of stars have to take at least 1,000 million years. But James Webb discovered galaxies with exactly that mass at crimson shifts of 9, 10, even 11. Those galaxies existed when the universe changed into less than 500 million years antique. Some seem as early as 300 million years after the Big Bang. Their mere existence challenges the timeline. One instance is a galaxy discovered at pink shift 11. The records indicates it contains 10 billion times the mass of our famous person inside the shape of stars and gas. This isn't a small galaxy. It is similar in mass to the massive Magellanic Cloud, one of the Milky Method's satellite galaxies. The problem is the age. At purple shift 11, the universe turned into most effective 400 million years old. Building 10 billion stellar hundreds in that time calls for superstar formation fees a ways higher than models predict. The galaxies are not just massive, they're also mature. Their spectra display symptoms of older stellar populations, which means the celebrities were around for a while. A few galaxies even display evidence of dirt which forms from supernova ejecta. Dust takes time to build up. Its presence suggests the galaxy has already long gone through a couple of cycles of megastar formation and dying. How did they develop so rapid? One idea entails extremely green big-name formation. Perhaps the primary galaxies transformed fuel into stars at prices 10 or 20 times higher than current galaxies. If celebrity formation became that green, galaxies may want to attain massive loads quickly. But this requires explaining why efficiency changed into so high. What situations inside the early universe made superstar formation so effective? Every other opportunity is that dark matter halos grew faster than current fashions recommend. If halos assembled greater fast, they might pull in gasoline quicker, accelerating galaxy growth. This can show up if darkish matter has properties we've got no longer accounted for, or if the early universe's density fluctuations have been more potent than we found out. Merges can also play a position. If small galaxies formed very early and merged hastily, they may integrate their loads into larger systems in much less time. But mergers alone likely can't explain the most huge galaxies. The merger fee could want to be surprisingly excessive, and there is not enough time for that many mergers to arise. A few scientists assume the observations is probably misinterpreted. The masses may be overestimated if the galaxies incorporate very bright stars or lively black holes that mimic the light of many stars. If that is proper, the real stellar mass could be decreased, making the galaxies less difficult. But spectroscopy normally policies this out. The mild from stars has a different signature than light from black holes, and maximum of these galaxies display stellar-ruled spectra. The invention of massive early galaxies is forcing a reconsider of galaxy formation fashions. The equations that describe how shape forms in the universe might want adjustment. The parameters that manage famous person formation might want changing. Or there is probably entirely new physics at play, something we've no longer taken into consideration due to the fact we by no means had observations this deep into the early universe. Each massive galaxy James Webb unearths provides to the puzzle. Each one pushes the limits of what should be viable, and each one shows the universe was more dynamic, more energetic, and more capable of rapid increase than we ever imagined. Keep a grain of sand at Palm's period toward the night sky. The area it covers carries over 10,000 galaxies. That is not an exaggeration. That is what James Webb's first deep field photo revealed whilst it stared at galaxy cluster SMACUR 723 for 12.5 hours. The picture covers a patch of sky so small you can block it with a pinhead. But inside that tiny slice, the universe reveals its genuine scale. Galaxies crowd the body, overlapping and intermingling. Some are vivid spirals with clean structure. Others are faint smudges slightly seen in opposition to the black history. A few are so remote their mild has traveled for over 13 billion years to attain the telescope. The galaxy cluster SMACUR 0723 sits approximately 4 billion light-years away. The cluster itself is massive, containing masses of galaxies certain together by means of gravity. The mixed mass of all those galaxies warps space-time round them, developing a gravitational lens. This lens bends and magnifies the mild from galaxies a long way in the back of the cluster, allowing James Webb to see items that would otherwise be too faint to detect. Gravitational lensing is one of the universe's herbal hints for revealing distant objects. Einstein expected it in his fashionable relativity equations. Large objects curve space-time, and light traveling through curved space-time follows an unethical direction. The result is just like how a picture lens bends mild to shape and picture. The galaxy cluster acts as a cosmic magnifying glass, bringing distant galaxies into view. Some of the galaxies inside the photo seem stretched and distorted, smeared into lengthy arcs via the lensing impact. These arcs are actually unmarried galaxies whose light has been bent across the cluster. By means of analyzing the distortion, astronomers can calculate the galaxy's distance and mass. The more distorted the picture, the more big the cluster and the farther away the heritage galaxy. The faintest objects within the image are also the oldest. Their light left them while the universe was less than 1,000 million years old. These galaxies seem crimson because their mild has been stretched with the aid of cosmic expansion. What turned into firstly ultraviolet radiation has shifted into infrared wavelengths. James Webb's sensors are tuned to detect precisely this kind of light, making it perfect for locating the universe's most ancient structures. Every galaxy inside the phono has its own records. A few are younger and actively forming stars. Others are old and demise, their stellar populations fading. Some have skilled mergers that twisted their shapes. Others grew in isolation, undisturbed for billions of years. The variety is impressive. No galaxies are identical. The deep area additionally indicates the big-scale structure of the universe. Galaxies are not allotted randomly. They cluster collectively in corporations and chains, forming a cosmic web. The net's filaments stretch across masses of millions of mild years with substantial empty voids in between. The SMACUR 723 cluster sits at a node in this net, a factor in which more than one filaments intersect. James Webb captured this image in 12.5 hours. The Hubble Space Telescope wished weeks to acquire similar intensity. This improvement in performance means James Webb can survey larger areas of sky in less time, discovering greater galaxies and building a more complete picture of cosmic records. the picture is simply the start. Astronomers will spend years reading it, measuring the properties of person galaxies, calculating distances, and reading how galaxy populations alternate over time. Each galaxy gives clues approximately celebrity formation, chemical enrichment, and the methods that power cosmic evolution. What makes this photograph profound is the reminder it presents approximately scale. That tiny patch of sky contains lots of galaxies. The complete sky carries over 40,000 rectangular stages. If each area has similar galaxy density, the observable universe carries trillions of galaxies. Trillions, each one potentially containing billions of planets. Each one a universe unto itself, packed with stars and worlds and mysteries we are able to by no means reach. The grain of sand is a metaphor, but it's also a fact. The universe's vastness is incomprehensible. We can capture it in pics. We can degree it with numbers. However, we can't really draw close it. The thoughts fails to preserve something so large. All we are able to do is marvel on the images and understand how small our corner of life absolutely is. Mild does now not travel in directly traces close to big gadgets. It follows the curvature of spaceme, bending around concentrations of mass. This bending is gravitational lensing, and it turns galaxy clusters into Hubble telescopes that reveal the universe's maximum distance structures. Galaxy clusters comprise heaps of galaxies, each contributing mass. Darkish matter, which outweighs seem be counted through 51, adds even extra mass without being visible. The combined gravitational area is giant, warping spaceme throughout hundreds of thousands of mild years. Whilst mild from galaxy passes close to the cluster, it gets deflected regularly in multiple instructions. The end result is that a single background galaxy can produce a couple of photos. The mild takes distinct paths around the cluster, arriving at our telescopes from barely unique angles. Each path creates a separate picture. Now and again these pics appear as arcs or jewelry surrounding the cluster. Other times they appear like disconnected fragments scattered across the sky. With the aid of measuring the positions and shapes of these photos, astronomers can reconstruct what the authentic galaxy appeared like and calculate its distance. Gravitational lensing additionally magnifies light. The bending impact concentrates photons, making the heritage galaxy appear brighter than without the lens. This magnification may be considerable, occasionally boosting a galaxy's brightness by means of factors of 10 or extra. Galaxies that might be too faint for James Webb to stumble on grow to be visible way to the lensing effect. One well-known instance is the cosmic horseshoe, a nearly complete ring shape through a far-off galaxy lensed by a foreground galaxy cluster. The ring isn't a bodily shape, it's miles a trick of light, the photograph of a single galaxy stretched and wrapped across the cluster's gravitational field. Without lensing, this galaxy might seem as a tiny faint smudge. With lensing, it becomes a brilliant arc visible throughout the sky. James Webb uses gravitational lensing to push its observations deeper than might otherwise be possible. By concentrated on galaxy clusters regarded to produce robust lensing results, the telescope can see galaxies from the primary few hundred million years after the Large Bang. Those galaxies are so distant and faint that they would be invisible without the magnification supplied via the clusters. One challenge with lensing is that it distorts the photograph. The galaxy's shape receives twisted and fragmented. Reconstructing the authentic look calls for state-of-the-art models that account for the cluster's mass distribution. Astronomers map the cluster's gravitational subject by reading how it lenses more than one background galaxies. Once they know the sphere's shape, they could reverse the lensing impact and determine what the galaxies really look like. Any other benefit of gravitational lensing is that it probes dark matter. The lensing power relies on the entire mass along the road of sight, including dark count. Via measuring the lensing effect, astronomers can map wherein darkish be counted is placed in the cluster. Those maps screen that darkish count bureaucracy dense concentrations on the cluster's center, surrounded by extra diffuse halos extending a long way past the seen galaxies. Now and again, gravitational lensing creates an unprecedented phenomenon known as an Einstein ring. This occurs whilst a background galaxy, the lensing object, and the observer are perfectly aligned. The mild from the background galaxy gets bent equally in all guidelines, forming a complete ring across the lensing object. Einstein rings are lovely and symmetrical, but they may be also scientifically precious. The ring's radius relies upon the lensing mass, imparting a particular measurement of the cluster's weight. The maximum effective lenses inside the universe are galaxy clusters inside the system of merging. When two clusters collide, their mixed mass creates an excellent, stronger gravitational subject. Those merges produce intense lensing outcomes that can magnify historical past galaxies by means of factors of 50 or more. James Webb has located numerous merging clusters, revealing galaxies that could be not possible to look some other manner. Gravitational lensing is one of the few tools that allows astronomers to observe the universe's earliest galaxies in detail. Without it, objects from the cosmic sunrise could continue to be invisible, too faint and too distant for even the maximum powerful telescopes to stumble on. The universe has provided us with Hubble magnifying glasses scattered throughout the sky, and James Webb is the usage of them to peer deeper into time than ever earlier then. A galaxy named Virgil regarded regular and seen and ultraviolet mild, young, quiet, forming stars at a modest fee. Then James Webb observed it in infrared. The galaxy converted. At its center sat a huge, closely obscured brilliant big black hollow pouring out extensive amounts of strength. The black hole turned into invisible in regular mild due to dirt. Thick clouds of dirt surrounded the black hollow, soaking up its ultraviolet and seen radiation. The dirt heated up and radiated the power as infrared mild, which James Nett's instruments are designed to come across. That is why the telescope can see from observatories omit. It looks wherein others can't. Virgil isn't on my own. James Webb has found several galaxies with hidden first-rate large black holes. Those objects appear calm and unremarkable while discovered in seen mild, but infrared observations monitor severe activity at their motive. The black holes are feeding hastily, pulling in gas and dirt, but the surrounding cloth blocks the mild from escaping invisible wavelengths. This discovery has principal implications for knowledge black hollow demographics. Previous surveys that trusted seen and ultraviolet light can also have missed a sizable fraction of active black holes. If many black holes are hidden at the back of dust, then the entire number of actively feeding supermassive black holes inside the universe is better than we idea. Why are these black holes so dusty? One cause is that they are nevertheless developing. Younger galaxies incorporate greater gas and dirt than older galaxies. The material that feeds the black hole additionally obscures it. As the black hole accretes count, the encompassing disk heats up and emits mild. However, before that light escapes, it hits dirt particles orbiting farther out. The dirt absorbs the mild and glows in infrared. Some other factor is geometry. If the dusty disk across the black hole is viewed facet on, the dirt blocks our view of the center. We see the galaxy's stars and gasoline, but the black hollow itself is hidden. Only by way of gazing in infrared, which penetrates dust extra without difficulty than seen light, can we detect the black hole's presence. Virgil's black hole is defined as overhuge. The black hollow's weight is higher than anticipated for a galaxy of Virgil's size. In most galaxies, the relevant black hole weighs about 50% of the galaxy's total stellar mass. In Virgil, the ratio is a whole lot higher. The black hole is disproportionately huge, suggesting it grew quicker than the surrounding galaxy. This raises questions about which comes first, the galaxy or the black hollow. Conventional fashions assume galaxies shape first and black holes grow internal them. Virgil indicates the other would possibly once in a while be proper. Perhaps the black hole forms early and grows rapidly, and the galaxy builds up around it over time. If this happens, we might expect to find galaxies like Virgil, wherein the black hollow dominates the mass. The invention additionally highlights the significance of wavelength observations. Looking at gadgets in most effective one sort of light gives an incomplete image. Virgil at one manner in seen light, and absolutely different in infrared. To understand the entire story, astronomers want statistics across the electromagnetic spectrum, from radio waves to gamma rays. Jamesnet's mid-infrared instrument become critical for revealing Virgil's hidden black hollow. This device operates at wavelengths between 5 and 28 micrometers, well beyond what seen-mild telescopes can see. At those wavelengths, dust turns into transparent, and the warmth from buried black holes will become visible. What number of extra hidden black holes are available? Nobody knows, but James Webb has surveyed a tiny fraction of the sky. As it maintains observations, extra galaxies like Virgil will in all likelihood be observed. Every discovery adds to our expertise of ways black holes and galaxies evolve together. The universe is complete of secrets and techniques, and many are hidden in the back of veil of dirt. James Webb is pulling back the one's veils one at a time, revealing the systems and methods that shape cosmic evolution. What we knew approximately galaxies is converting. The antique photo primarily based on seen light by myself is incomplete. The brand new picture, enriched by infrared observations, is stranger and more complicated than we imagined. James Webb found a trouble. Early galaxies are too brilliant. No longer only a little brighter than predicted, however 10 times brighter. This isn't always a minor discrepancy. It means something fundamental is inaccurate with the models that describe how galaxies shape and evolve within the first billion years after the huge bang. The models are sophisticated. They comprise darkish depend, gasoline dynamics, famous person formation, and comments from supernovas and black holes. Cosmologists run those models on supercomputers, simulating billions of years of cosmic records. The simulations predict what number of galaxies need to exist at exceptional instances, and the way shiny the one's galaxies must be. Earlier than James Net, the predictions matched observations fairly nicely. Hubble determined galaxies inside the early universe, and their numbers and brightness aligned with expectancies. Then James Webb seemed deeper and the photo changed. The telescope revealed galaxies everywhere, a long way greater several and luminous than the simulations expected. What makes early galaxies so shiny? One opportunity is famous person formation performance. Perhaps the first galaxies converted fuel into stars more effectively than modern galaxies. If every fuel cloud that collapsed formed stars, as opposed to being disrupted by turbulence or feedback, the galaxy could produce extra stars in less time. Extra stars suggest extra mild. Any other opportunity entails the styles of stars being formed. If early galaxies produced a better percentage of huge stars, they would be brighter. Big stars shine a long way extra intensely than smaller stars. A star 100 times heavier than ours may be 1 million times brighter. If the stellar mass characteristic in early galaxies turned into skewed toward heavy stars, the overall luminosity could boom dramatically. Brilliant large stars may also contribute. These hypothetical gadgets might be masses or lots of times heavier than traditional stars. They could shine with the mild of entire galaxies dominating the total luminosity. If even a small fraction of stars in early galaxies had been top-notch huge, they might give an explanation for the excess brightness. But exceptional big stars are theoretical and have now not been confirmed. Black holes would possibly play a function. 2. Lively outstanding huge black holes emit significant quantities of mild as they accrete count. If early galaxies contained more active black holes than expected, their mixed mild may want to boost the galaxy's total luminosity. Some of the brightest early galaxies do show signs of black hollow hobby, even though now not all. The brightness trouble also influences predictions about reionization, the manner with the aid of which ultraviolet light from the first stars ionized the universe's hydrogen gasoline. If early galaxies have been brighter, they produced extra ultraviolet mild, probably completing reionization in advance than models predict. Observations of the cosmic microwave history advise reionization ended round 400 million years after the massive bang. Brighter galaxies might match this timeline better. Some other perspective is dirt. The fashions anticipate early galaxies include little dirt due to the fact dirt bureaucracy from supernova ejector which takes time to build up. However, some James Net observations display dirt in galaxies less than 500 million years antique. If dust formed quicker than predicted, it may have an effect on the galaxy's brightness. Dust absorbs ultraviolet mild and remits it as infrared, changing the spectral form and doubtlessly making galaxies seem brighter in certain wavelengths. The cosmological parameters themselves is probably incorrect. The models use values for dark count number density, darkish strength electricity, and the initial density fluctuations seeded via the massive bang. If any of those values are incorrect, the predictions fail. Adjusting the parameters would possibly convey the models into better agreement with observations, even though this would have effects for other predictions. Some scientists suppose the observations is probably misinterpreted. The measured brightness will be artificially inflated by way of gravitational lensing or confusion with foreground gadgets. But spectroscopy commonly guidelines this out. The red shifts are actual and the galaxies are really distant. The anxiety among fashions and observations is one in all the biggest surprises from James Webb's first few years. It shows our knowledge of galaxy formation is incomplete. Something took place inside the early universe that we have no longer accounted for. Some process made galaxies brighter, quicker developing, and extra severe than we anticipated. Until we discern out what that system is, the puzzle stays unsolved. Mild modifications as it travels through increasing area. This isn't a minor impact. It is the reason James Webb can see the early universe at all. Without growth stretching light into infrared wavelengths, the most remote galaxies might remain invisible all the time. When a galaxy emits light, that light has a particular wavelength, decided by the atoms producing it. Hydrogen emits a brilliant line at 121 nanom deep inside the ultraviolet. Oxygen emits strains inside the seen variety. Those wavelengths are fixed by means of physics. They do now not trade based totally at the supply. But, as mild travels via space, the fabric of area itself expands. This expansion pulls at the light waves, stretching them to longer wavelengths. Ultraviolet light turns into seen light. Visible light will become infrared. Infrared turns into far infrared. The farther the light travels, the more it gets stretched. Astronomers degree this stretching using pink shift, denoted by using the letter Z. A crimson shift of 1 manner the mild's wavelength has doubled. A pink shift of 2 way it has tripled. MZ14, the maximum distant galaxy ever located, has a red shift of 14, 44. Its light has been stretched via a component of 15, 44. Ultraviolet mild that left at 120 nm arrives at Earth at 1869 nanom deep within the infrared. That is why older telescopes couldn't find these galaxies. The Hubble Space Telescope operates often in seen and close to infrared wavelengths, overlaying kind of 400 to at least 600 nanom. Galaxies with crimson shifts above 7 emit most of their light past Hubble's variety. They're invisible to it. James Net become designed particularly to clear up this trouble. Its instruments caudal wavelengths from 600 nanom to 28,000 nanom spanning seen red light via mid-infrared. This variety captures light from galaxies at any pink shift as much as about 20, past crimson shift 20. Even James Net struggles because the mild shifts into wavelengths its detectors cannot see. The growth of area isn't like gadgets transferring via area. It is space itself growing. Imagine dots on a balloon's floor. As you inflate the balloon, the dots move aside, no longer due to the fact they're visiting throughout the rubber, however because the rubber among them is expanding. Light traveling through expanding area reports the identical effect. The gap between the mild wave's peaks grows, stretching the wavelength. This expansion is accelerating. Dark electricity drives the acceleration, pushing area to expand faster and quicker. Galaxies some distance from us are receding at speeds that exceed the velocity of mild. This does not violate relativity, due to the fact the galaxies aren't shifting via area quicker than light. Space among us and them is growing quicker than light can go it. For the most distant galaxies, their light spent over 13 billion years visiting to us. Throughout that point, the universe expanded extensively. Space that became an awful lot smaller when the light started out its journey is now hugely large. The mild waves stretch together with that enlargement, reworking into infrared radiation by the point they attain James Webb's mirrors. Understanding purple shift permits astronomers to degree distances with precision. In case you realize a galaxy's red shift, you could calculate how a long way away its miles and how long ago its light became emitted. This turns the telescope right into a time system. Higher pink shift equals more distance equals farther returned in time. The maximum severe crimson shifts James Webb has detected are around 14 to 15. These correspond to galaxies seen as they existed only a few 100 million years after the Big Bang. The light from these galaxies has traveled across 99% of the observable universe to reach us. It's been stretched by using factors of 15 or more, shifting totally out of the seen spectrum. Without this stretching, we should in no way see the early universe. The galaxies could emit ultraviolet light that Earth's ecosystem absorbs before it reaches the floor. Even space-based telescopes operating in ultraviolet couldn't see them due to the fact the distances are too exceptional and the mild too faint. Purple shift transforms that ultraviolet light into infrared, a wavelength variety wherein James Webb excels. The universe is revealing itself to us, not inside the light it at first emitted, however inside the transformed, stretched, ancient radiation that has crossed billions of light years of expanding space. Each photon James Webb collects contains the signature of cosmic expansion imprinted on its wavelength. There may be a galaxy in which the black hollow outweighs the stars, no longer with the aid of a small margin. The black hollow's mass equals or exceeds the combined mass of every superstar inside the galaxy. This ought to now not be feasible. Galaxies are imagined to dominate. Black holes are alleged to be minor additives dwelling at the middle, but contributing little to the total mass. CAN country RDZ86 breaks this rule. The galaxy's stars weigh a few 100 million times what our big name weighs. The primary black hollow weighs as a minimum that a lot, probably more. The ratio is completely inverted from what we see in modern galaxies. It's far as though the black hole shaped first, and the galaxy is an afterthought. This ratio is referred to as the black hollow to stellar mass ratio. Inside the Milky Manor, the important black hole weighs approximately 4 million times what our big name weighs. A galaxy's general stellar mass is around 60 billion times our star's mass. The ratio is roughly 1 to 15,000. The black hollow is a tiny fraction of the full. In usual huge galaxies, the ratio is higher. The valuable black holes weigh greater, every so often reaching billions of solar loads. But the galaxies also weigh more, preserving a comparable percentage. The heaviest black holes sit inside the heaviest galaxies. The connection holds throughout billions of years of cosmic time. Except in the early universe, James Webb has found multiple galaxies wherein the black hole dominates. Those little pink dots continuously show black holes which might be too large for their hosts. The relationship among black hollow mass and galaxy mass appears broken inside the first billion years after the large bang. How did this happen? One concept shows black holes fashioned from big fuel clouds that collapsed at once without forming stars first. Those direct crumble black holes could begin heavy, maybe thousands or tens of lots of instances our star's mass. As soon as shaped, they would begin accreting matter swiftly, developing even large. Meanwhile, the surrounding gasoline could shape stars more slowly. The black hollow receives a head start and the galaxy by no means catches up. Another idea involves exquisite large stars. If the first stars were masses or thousands of times heavier than traditional stars, they might fall apart into massive black holes after they died. Those seed black holes could already be huge, giving them a bonus within the race to build up mass. A third opportunity is that superstar formation turned into suppressed close to the black hole. As the black hollow feeds, It emits severe radiation and powerful winds. This strength can warm and blow away nearby gas, stopping it from collapsing into stars. The black hole grows by ingesting the gas that would in any other case form stars, naturally main to excessive black hole to stellar mass ratio. The invention of over-huge black holes has implications for information how present-day quasars shaped. Quasars are the brightest gadgets inside the universe. Powered with the aid of top-notch large black holes weighing billions of instances our star's mass. These quasars exist at redshifts as excessive as 7. That means they formed whilst the universe changed into much less than 1 billion years vintage. Developing black holes that large that fast requires excessive feeding charges or massive seed black holes. If early galaxies robotically produced over large black holes, then the building blocks for quasars had been in place very early. The little red dots that James Webb sees might be the progenitors of quasars, caught in an early section of their evolution, before the host galaxy has grown to match the black hole's mass. Over the years, those systems likely developed into greater balanced configurations. The black hole's comets ultimately slows its personal growth by using heating and expelling close-by gas. Meanwhile, the galaxy keeps accreting gasoline from large distances, developing its stellar mass. Finally, the black hole to stellar mass ratio decreases, coming near the values we see in present-day galaxies. What this tells us is that galaxy and black hole boom are not usually synchronized. In the early universe, black holes once in a while got beforehand. They grew faster than their hosts, dominating the mass price range. This is opposite to what takes place in the neighborhood universe, wherein galaxies grow first and black holes stay small. The universe's kids became a time of imbalance and extremes. Forces that later settled into equilibrium had been nonetheless competing. Black holes had blessings they later misplaced. And the proof is scattered throughout the shape of galaxies, wherein black holes rule and stars are an afterthought. For masses of millions of years after the massive bang, the universe became darkish, absolutely darkish. No stars existed. No galaxies. Just impartial hydrogen gasoline filling all of space, cooling because the universe extended. This era is referred to as the cosmic dark ages. And it ended when the primary stars ignited. That moment while mild flooded the cosmos for the first time is called the cosmic dawn. It came about roughly 150 to 300 million years after the massive bang. Gravity pulled gas into dense clumps. Pressure built, temperatures rose, fusion ignited, and stars started to shine. The primary stars were exceptional from contemporary stars. They fashioned from pure hydrogen and helium without heavier elements. This affects their structure and evolution. Without metals to facilitate cooling, the fuel clouds could not fragment into small pieces. They collapsed into larger, more massive objects. The first stars have been in all likelihood 50 to several hundred times heavier than our famous person. These huge stars burned tremendously hot and vivid. They emitted large amounts of ultraviolet radiation, a ways greater than smaller stars produce. This radiation started out to ionize the encompassing hydrogen fuel. Neutral hydrogen atoms absorbed the ultraviolet photons, dropping their electrons and becoming ionized plasma. A bubble of ionized gas fashioned round each superstar, growing larger as extra photons streamed out. Before everything, those bubbles had been isolated. Stars shaped in scattered places across the universe, each creating its very own ionization region. The areas between remained dark and impartial. Over time, more stars fashioned, more bubbles seemed. Subsequently, the bubbles started out to overlap, merging into larger ionized areas. This system is known as reionization. It converted the universe from a neutral fuel, fill void into an ionized plasma. Reionization took masses of tens of millions of years to complete. Early on, handiest small patches of space have been ionized. By way of about 400 million years after the Big Bang, most of the universe were reionized. The cosmic dawn transitioned into the cosmic midday, and technology of extreme celebrity formation and galaxy boom. James Webb is staring at galaxies from the cosmic sunrise. These galaxies include the descendants of the first stars. A few may nonetheless harbor some populous 3 stars, although maximum have already died. What we see in those galaxies is the early segment of structure formation, whilst the universe became simply starting to light up. The mild from those galaxies is faint and redshifted. It has traveled across 13 billion light-years of expanding space to attain us. When the mild left the one's galaxies, the universe became younger and small. Now it is antique and good-sized. The light includes statistics approximately what conditions were like at some stage in the cosmic dawn. Encoded in its spectrum and brightness, observations of the cosmic dawn help answer essential questions. How quickly did the primary stars shape? How big had been they? How correctly did they ionize the encompassing gasoline? Those questions have an effect on our know-how of the whole thing that came after. The first stars set the stage for all next cosmic evolution. Reionization also affected how later galaxies shaped. Once the universe was ionized, small clumps of gas couldn't without problems crumble to form stars. The ionized gas has gravistress, resisting gravitational collapse. This suppressed superstar formation in low-mass halos, preventing the formation of very small galaxies. Handiest halos above a sure mass threshold should preserve forming stars correctly. This threshold explains why modern dwarf galaxies are much less commonplace than dark matter simulations expect. Darkish count halos of all sizes should exist. However most effective, the bigger ones can shape seen galaxies in an ionized universe. The smallest halos continue to be darkish, filled with gas that never cooled enough to shape stars. The cosmic sunrise became a turning point. Before it, the universe became easy. Hydrogen, helium, darkish count number and radiation. After it, the universe became complicated. Stars, galaxies, heavy elements, and the structures we see nowadays. That transition passed off in just a few 100 million years. A brief moment in cosmic records. James Webb is witnessing the aftermath of that transition. Every galaxy it sees from the primary billion years incorporates echoes of the cosmic dawn. The light of the first stars, now lengthy useless, fashioned the galaxies we have a look at today. Their legacy is written inside the distribution of elements, the shape of galaxies, and the ionization country of intergalactic gas. The universe went from darkness to light within the blink of a cosmic eye. And we're only now seeing the glow of that awakening. 13 billion years not on time by the time it took mild to go the universe. Galaxy clusters are most important gravitationally bound structures within the universe. They comprise hundreds of galaxies held collectively by way of gravity. The combined mass is full size, weighing as a good deal as a quadrillion stars. That mass warps spacetime so critically that it bends light from historical past items, developing a Hubble telescope. This effect is called strong gravitational lensing. Mild from a far-off galaxy passes via the curved spacetime round a cluster. The curvature deflects the light, converting its direction. From our attitude, the galaxy's image seems distorted, magnified, and occasionally improved. We see arcs, jewelry, and a couple of copies of the same item. Astronomers use those Hubble telescopes to observe galaxies that might otherwise be invisible. The cluster's gravity acts like a lens, focusing mild and boosting its brightness. Some galaxies get magnified via elements of 10, 20, even 50. Gadgets too faint for James Webb to come across on its very own turn out to be visible way to the cluster's amplification. One famous lensing cluster is Abell 2744, also referred to as Pandora's cluster. It sits about 3.5 billion light-years away and includes loads of galaxies. The cluster's mass distribution is complex because it's shaped from multiple smaller clusters that merge collectively. This complexity creates strong lensing outcomes throughout a wide area, making it a perfect target for deep surveys. James Webb has located Abell 2744 appreciably. The pics found out dozens of lensed galaxies, many from the early universe. A few seem as long arcs stretched throughout the cluster. Others show up as a couple of photographs of the equal galaxies scattered around different positions. By means of analyzing these pics, astronomers can measure the cluster's mass distribution and decide the houses of the lensed galaxies. Any other effective lens is SMACS SOAR 723, the goal of James Webb's first deep field picture. This cluster created numerous lensed arcs seen within the image. Some of the arcs correspond to galaxies at red shifts above 10, setting them within the first 500 million years after the Big Bang. Without the cluster's magnification, these galaxies might be too faint to look. The lensing effect depends on precise alignment. The historical past galaxy, the cluster, and the observer ought to be nearly in a directly line for sturdy lensing to occur. If the alignment is best, the result may be an Einstein ring, a whole circle of mild surrounding the cluster. Most alignments aren't ideal, producing partial arcs alternatively. Clusters also produce a phenomenon referred to as susceptible lensing. This influences galaxies that are not perfectly aligned. Their pix gets slightly distorted, stretched in precise guidelines by means of the cluster's gravitational area. In my view, those distortions are diffused. However, via measuring the shapes of many heritage galaxies, astronomers can map the cluster's mass distribution together with the dark matter that makes up maximum of the cluster's mass. Gravitational lensing reveals dark depends presence, despite the fact that dark, remember, does now not emit mild. The lensing energy depends on general mass, visible and invisible. With the aid of comparing the lensing impact to the mass of seen galaxies, astronomers calculate how an awful lot dark matter is gift. The solution is usually 5 to 6 times greater dark, remember, than everyday depend. A few clusters create extraordinarily uncommon occasions referred to as first-rate lensing. This occurs when multiple clusters align along the identical line of sight, every contributing to the lensing impact. The blended magnification can reach factors of 100 or greater. Those activities are so uncommon that most effective a handful are known. However, they permit James Net to see galaxies from even earlier in cosmic history. The disadvantage of gravitational lensing is that it distorts the galaxy's shape. To look at the galaxy's real structure, astronomers should version the lensing impact and reverse it. This requires detailed know-how of the cluster's mass distribution. Teams create sophisticated fashions that account for the positions and masses of character cluster galaxies, in addition to the dark matter halos surrounding them. Nature supplied these cosmic magnifying glasses scattered at some stage in the universe. And they be not located randomly. Clusters shape at nodes in the cosmic web in which dark relay filaments intersect. These places pay attention mass, creating the robust gravitational fields wished for lensing. By way of targeting clusters, James Webb maximizes its ability to look the early universe. Each important lensing cluster has been discovered through James Webb, Able 2744, SMACS SOAR 723, MACS SOAR 460s, and dozens of others. Each remark famous new lensed galaxies pushing the observational frontier farther lower back in time. The clusters are doing paintings that no telescope by myself ought to accomplish, bringing the universe's earlier structures into view. The mild we see from early galaxies shows us stars that not exist. The one stars burned fused and exploded billions of years ago. What stays is their historical mild, photons which have been traveling via area for over 13 billion years. Each photon contains facts approximately the celebrity that emitted it. Whilst a celebrity paperwork, it creates a specific sample of mild. Hot, younger stars emit more often than not ultraviolet and blue light. Cooler, older stars emit crimson and infrared mild. Through analyzing the spectrum, astronomers can decide the celeb's temperature, age, and chemical composition. This works even if the star is billions of mild years away. James Webb spectrographs split mild into its issue wavelengths, developing distinct spectra. These spectra display emission traces from hydrogen, helium, oxygen, carbon, and other factors. Every detail leaves a unique fingerprint. The pattern of traces exhibits what the galaxy is manufactured from and how its stars are evolving. Early galaxies show sturdy hydrogen and helium traces constant with stars forming from primordial gas. Some additionally show carbon and oxygen traces, indicating that as a minimum one technology of stars has already died and enriched the gasoline. The presence of those heavier elements tells us how many stellar generations have surpassed since the galaxy fashioned. Superstar formation is an ongoing method. Fuel clouds crumble, fragment into smaller pieces, and ignite as new stars. This occurs continuously in energetic galaxies. The celebs we see in James Internet images aren't the unique stars that fashioned. They are later generations constructed from gas enriched by earlier supernovas. Every generation provides greater heavy elements. The primary era, population 3 stars, produced carbon, oxygen, and some nitrogen. Once they exploded, those factors blended into the encompassing gas. The second one, technology shaped from this material, fusing those factors into heavier ones like silicon and iron. The 33 technology included even greater metals. By the point we see a galaxy at Crimson Shift 10, it has already long passed through a couple of cycles. The celebs presently shining are not pristine. They incorporate metals cast in earlier stars. The amount of metallic reveals how many cycles have came about. Excessive metallicity method, many generations. Low metallicity manner, the galaxy remains young. The light from these stars left the galaxy whilst the universe became less than 500 million years old. It traveled via expanding space for 13.3 billion years. All through that journey, the light we're given stretched from ultraviolet into infrared. The stars emitting it have long on account that died. A few exploded as supernovas, others quietly diminished into white dwarfs. A few collapsed into black holes. What we take a look at is a picture of the past, the galaxy frozen in time at an early level of its evolution. We cannot see what took place to it later on. The galaxy these days, if it nonetheless exists, is likely much large and older. It may have merged with different galaxies, reworking into something absolutely extraordinary. However, we will never see that destiny kingdom, due to the fact the light displaying it has not reached us yet. This put-off creates an unusual state of affairs. We can study galaxies at multiple ranges in their lives by looking at different distances. Close-by galaxies show us what developed systems seem like nowadays. Remote galaxies display us what young systems seemed like billions of years ago. Via combining observations throughout distances, astronomers construct a timeline of galaxy evolution. The stars forming in early galaxies are the ancestors of stars that exist nowadays. The gasoline that shaped them sooner or later became a part of later galaxies via mergers and accretion. Some of that gas may have ended up inside the Milky Way. A few may have fashioned our star and the planets round it. The atoms for your frame had been cast in stars that lived and died billions of years in the past. James Webb sees the light from those ancient stars, photons that escaped simply after the cosmic dawn. Each photon is a messenger from the beyond, wearing news of activities that passed off while the universe turned into young. The celebrities are gone. The galaxies have changed. What stays is the light traveling perpetually through the void until it sooner or later arrives at a telescope mirror. Black holes have a growth hassle. They cannot eat quicker than a sure fee without choking themselves. The limit is referred to as the Eddington restrict, and it depends on radiation stress. As B counted falls into a black hole, it heats up and emits mild. That mild pushes outward, counteracting gravity. If the light is strong sufficient, it blows away incoming depend, restricting how speedy the black hole can grow. The math is simple. A black hole weighing 1 million times our star's mass can grow via about 1% every million years on the Eddington limit. To attain 1 billion times our star's mass starting from 100 sun mass seed takes over 700 million years of non-stop feeding at maximum rate. This is slightly sufficient time if the black hole forms without delay after the massive bang and feeds non-stop. Yet, James Webb unearths black holes weighing hundreds of thousands and thousands or billions of sun masses at red shifts above 7. These black holes existed while the universe became less than 700 million years vintage. The timeline is just too short. Even feeding on the maximum theoretical charge, beginning from stellar mass seeds, they ought to not be that big, but this indicates both the seeds have been larger than anticipated or the increased fee handed the Eddington restriction. both opportunities undertaking widespread models. Huge seed black holes require special formation mechanisms like direct collapse or terrific huge stars. Remarkable Eddington accretion requires conditions that triumph over radiation strain. A few models suggest that black holes, shaped from collapsing fuel clouds, as opposed to Death Stars. If a huge cloud of gas weighing tens of hundreds of times our stars, mass collapsed immediately right into a black hollow without forming stars first, it would create a heavy seed. This offers the black hollow a tremendous head begin. Developing from 10,000 Sun hundreds to 1 billion takes much less time than developing from 100. Direct fall apart requires specific situations. The gasoline must be steel, unfastened because metals help fuel cool, allowing it to fragment into stars before collapsing completely. The fuel should additionally be uncovered to a robust radiation field that forestalls hydrogen molecules from forming. Without molecules, the gas cannot cool successfully, forcing it to disintegrate right into an unmarried huge item. Those conditions might have been not unusual within the early universe. The primary stars produced intense ultraviolet radiation that saved close-by gas clouds hot. As these clouds collapsed, they could shape direct disintegrate black holes. If this befell frequently, the universe might have many heavy seed black holes equipped to develop into exceptional large giants. Instead, fantastic massive stars could have fashioned. Those stars might weigh loads or lots of instances our star's mass. They might burn through their fuel in a few million years and collapse into huge black holes. These seed black holes could already weigh hundreds of sun masses, again supplying a head begin. The hassle with each theories is that we have no direct proof for either. Direct collapse black holes and extraordinary huge stars are theoretical. James Webb has no longer located definitive examples of either till we study them forming or discover their signatures in early galaxies. They remain speculative answers. Superb Eddington accretion is extra practicable due to the fact we've got discovered it in at the least one case. A YF68 feeds at over 40 instances. The Eddington limit. If such episodes were not unusual within the early universe, black holes could develop a lot quicker than widespread fashions permit. A few million years of first-rate Eddington feeding could upload as plenty mass as tens of thousands and thousands of years at regular costs. The seas is that tremendous Eddington episodes are in all likelihood quick-lived. The black hole rapidly consumes nearby gas, and without a non-stop supply, the feeding charge drops. For this to solve the growth trouble, the universe must deliver gas to black holes efficiently and often. Merges among gas-rich galaxies might offer this delivery mechanism, triggering bursts of speedy accretion. Some other perspective is that black holes grew during the cosmic dark, a long time earlier than the first stars fashioned. If primordial black holes existed rapidly after the Big Bang, they could have had extra time to develop. A black hollow forming 1 million years after the huge bang profits an additional 150 million years of increased time in comparison to at least one forming after the primary stars ignited. Primordial black holes are debatable. They require specific situations at some point of the Big Bang to form, and maximum fashions do not produce them in massive numbers. However, in the event that they exist, they elegantly solve the growth problem with the aid of giving black holes greater time. The invention of over-large black holes is forcing theorists to revisit assumptions. Something approximately the early universe enabled fast black hollow boom. Both the seeds have been heavier, the feeding fees have been higher, or the timelines were longer than we notion. Each possibility calls for rethinking fundamental factors of ways black holes form and evolve. James Internet's first deep field photo isn't only a photograph. It's far a timeline. The image indicates galaxies from multiple eras, each visible at a distinctive distance. Nearby galaxies appear as they regarded some billion years in the past. The farthest galaxies appear as they existed over 13 billion years in the past. The whole records of the universe is compressed into one body. The photo required 12.5 hours of commentary time. James Webb stared at galaxy cluster SWEX-73 gathering photons separately. The longer the publicity, the extra faint light collected. Galaxies too dim to locate in quick exposures have become seen after hours of integration. The depth of the photograph is measured by value. Astronomers use a logarithmic scale in which every 5 magnitudes represents a thing of 100 in brightness. The faintest objects in the SMAC ZOR-723 photo attain magnitude 31 in infrared wavelengths. This is 100 million instances fainter than the faintest stars seen to the naked eye below best conditions. At these severe depths, nearly every speck of light is a galaxy. Stars are too faint to look at those distances. What appears as tiny dots or smudges are entire galaxies containing billions of stars. The quantity of galaxies inside the photograph approaches 10,000. Each one is a complete global separated from us through unfathomable distances. The photo indicates structural range. Spiral galaxies with defined fingers. Elliptical galaxies which are smooth and featureless. Irregular galaxies with chaotic shapes. Merging galaxies caught inside the act of collision. Each morphological type is represented, demonstrating the style of paths galaxies can take at some point of their evolution. Color within the image corresponds to wavelength. Blue represents shorter infrared wavelengths. Crimson represents longer wavelengths. The color of each galaxy famous its distance. Nearby galaxies appear blue due to the fact their light has now not been stretched lots. Distant galaxies seem crimson due to the fact their light has been redshifted extensively. The reddest items are the farthest, courting back to while the universe changed into much less than 1 billion years vintage. Some galaxies seem multiple times due to gravitational lensing. The cluster's mass bends mild from background galaxies, creating a couple of images. These duplicates are seen as arcs or distorted shapes around the cluster center. With the aid of measuring the separation between pictures, astronomers calculate the cluster's mass, together with its darkish remember content material. The picture also captures galaxies inside the cluster itself. These are the intense big galaxies near the photograph center. They sit down about 4 billion light-years away, a great deal nearer than the heritage galaxies. The cluster fashioned from merges of smaller galaxy companies over billions of years. Its present-day nation represents a mature huge shape. Between the cluster and the maximum remote galaxies lie intermediate distance items. Those galaxies existed at numerous instances among 4 billion and 12 billion years in the past. They show what galaxies gave the look of during exclusive evolutionary stages. A few are actively forming stars. Others have completed big-name formation and are fading. The variety illustrates how galaxy populations exchange through the years. What makes this picture traditionally considerable is that it surpassed all preceding deep fields in each depth and coverage. Hubble's private images required weeks of statement time and protected smaller regions. James Webb executed similar intensity in hours, opening the opportunity of mapping large regions of sky to comparable sensitivity. The clinical price lies inside the records. With heaps of galaxies visible, astronomers can measure how galaxy houses alternate with distance and time. They are able to be counted how many galaxies existed at one-of-a-kind epochs. They could observe the distribution of galaxy sorts and how it developed. These measurements constrain models of galaxy formation and test cosmological theories. Every galaxy within the photo has a story, so that it will by no means be completely instructed. We see them at 1 second of their history, frozen by the time it takes mild to tour. We do now not know what passed off earlier than or after. We cannot follow their evolution in real time. All we've got is this photograph, a single body from a cosmic film spanning billions of years. The deep area reminds us of our area in the universe. We are observers on one small planet, searching out at structures so widespread we are able to barely realize them. The mild from those galaxies has traveled longer than our species has existed. It started out its journey when the universe changed into young, and it arrives now to be captured by sensors fabricated from atoms forged in ancient stars. Every few months, James Webb breaks its personal distance file. a galaxy is found at redshift 13, then 14 and 1444. Every discovery pushes our view deeper into the past, towards the Big Bang itself. The development appears relentless, as if there may be no limit to how far back we can see. Purple shift measures how a lot mild has been stretched by using cosmic enlargement. Higher purple shift method, extra distance and earlier time. A purple shift of 1 corresponds to looking lower back approximately 7 billion years. Crimson shift 6 corresponds to 7 billion years ago, whilst the universe turned into handiest about 800 million years old. Red shift 14 corresponds to 280 million years after the huge bang. Every increment in pink shift turns into more difficult to gain. Going from redshift 0 to at least 1 is particularly easy. Many galaxies exist at that distance. Going from 13 to 14 is difficult. Galaxies are rare at the one's distances and their light is extremely faint. Locating them requires surveying massive areas of sky or watching small regions for extended durations. The modern file holder is MUM Z14 at redshift 1444. This galaxy changed into now not the first candidate determined at excessive crimson shift. Several other items confirmed comparable colors, suggesting extreme distance. But MUM Z14 became the first to have its pink shift confirmed spectroscopically. Without spectroscopy, pink shift estimates are uncertain. An item that appears distant based on its color can be a more in-depth galaxy with uncommon residences. Spectroscopic confirmation calls for detecting emission or absorption lines within the galaxy spectrum. Those lines correspond to precise factors and feature recognized wavelengths. By measuring wherein these traces appear within the observed spectrum, astronomers calculate how lots the mild has been redshifted. This gives a specific distance size. James Internet's near-infrared spectrograph is designed for this challenge. It can have a look at faint galaxies and extract spectra even when the objects are slightly seen. The tool splits light into loads of individual wavelength channels, growing a detailed spectrum displaying precisely where emission traces appear. Earlier than James Net, the highest showed crimson shift changed into round 11 to 13, accomplished by way of Hubble and ground-based telescopes. These galaxies existed about 400 million years after the Large Bang. James Webb has extended the file by using more or less 100 million years, achieving return to 280 million years put up huge bang. Is there a restriction to how some distance we will see? Theoretically, yes. The earliest galaxies should have fashioned sometime after the primary stars ignited, which came about around 150 to 200 million years after the Large Bang. Earlier than that, there had been no stars, so no galaxies. James Webb is drawing close this restriction. Another aspect of indistance would position us on the earliest feasible galaxies. However, finding the one's earliest galaxies is hard. The universe was smaller and denser lower back then, meaning galaxies have been probable smaller and fainter than the ones we've determined to date. Detecting them calls for longer publicity times and large survey regions. The Nancy Grace Roman Space Telescope, launching in 2027, will help by means of surveying plenty larger regions of sky than James Internet can. Every report, breaking discovery generates excitement and questions. How did galaxies shape so quickly? Why are they brighter than anticipated? What approaches enabled speedy star formation within the early universe? Every new galaxy offers statistics to check theories and refine fashions. The chase for better purple shifts isn't always just about statistics. It is about understanding the universe's infancy. The primary galaxies seeded all subsequent shape. They produced the first heavy elements. They ionized the universe. They set the degree for everything that got hereafter. Staring at them at once answers essential questions about cosmic origins. James Webb will likely keep breaking its very own records for years. As more survey data will become available, astronomers will discover even greater remote candidates. Spectroscopic comply with UP will confirm or rule out each one. The Crimson Shift report will inch upward, drawing close the theoretical limit. In the end, we will reach a factor in which galaxies sincerely do now not exist farther back. we will be searching on the cosmic dawn itself, the instant whilst the first stars ignited and light flooded the universe for the first time. That moment is inside attained now, simply past the present-day observational frontier. James Webb has found out a universe more complex and dynamic than everyone anticipated. Galaxies forming quicker, black holes growing larger, systems performing earlier. Every discovery demanding situations our fashions and expands our expertise of cosmic records. What does all this mean for us? For humanity, for our location in this impossibly widespread universe? First, it approach we are more youthful than we idea. Not individually, however collectively as a species linked to the cosmos. The atoms in our bodies have been cast in stars that lived and died billions of years ago. The ones stars shaped in galaxies just like the ones James Webb observes. The iron in our blood came from supernovas. The carbon in our DNA got here from stellar nucleosynthesis. We're made of stardust, literally composed of factors created in the early universe. The discoveries also display how unique our moment in time is. We live 13.88 billion years after the massive bang, in a universe that has matured and evolved. The chaotic, violent early universe is long gone. Star formation has slowed. Galaxy merges have decreased. The universe nowadays is calmer, greater dependent, extra hospitable to lifestyles. If we existed throughout the cosmic dawn, situations could have been a ways more excessive. Second, the discoveries emphasize scale. The universe includes trillions of galaxies. Every galaxy consists of billions or trillions of stars. Lots of those stars have planets. The range of potentially livable worlds exceeds comprehension. If even a tiny fraction of those worlds increase lifestyles, the universe may be teeming with it. We aren't special in phrases of place or fort. We're one planet among endless others. But we are also precise in our capability to look at and understand the cosmos. No other species on the planet has built telescopes or evolved physics. No different acknowledged existence has deciphered the universe's history or measured its age. Intelligence capable of medical discovery may be not unusual inside the universe, or it is able to be highly rare. We do now not know. What we do recognize is that we have it, and we are the use of it to discover our origins. 033. The discoveries display how tons we nonetheless do not apprehend. Darkish matter makes up most of the universe's mass, and we have no idea what it's for. Dark electricity drives cosmic growth, and we do not recognize its nature. The Hubble tension shows our cosmological model is incomplete. Remarkable massive black holes develop faster than models expect. Galaxies shape earlier and brighter than simulations allow. Each answer increases new questions. That is the nature of science. We construct fashions to give an explanation for observations. New observations task the one's models. We revise the models, making them more accurate. Then new observations challenge the revised models. The procedure repeats endlessly. We asymptotically technique fact without ever absolutely attaining it. Every era of scientists gets nearer. However, there may be always extra to examine. Fourth, the discoveries remind us of our cosmic insignificance. We stay on a tiny planet orbiting an average famous person in an regular galaxy in an unexceptional part of the universe. Our galaxy is certainly one of trillions. Our megastar is certainly one of hundreds of billions in that galaxy. Earth is one in all probably billions of livable planets simply within the Milky Way. The scale dwarfs us. Yet this insignificance is also freeing. The universe does no longer revolve round humanity. Cosmic events spread consistent with physical legal guidelines that do not care about us. Black holes merge. Galaxies collide. Stars explode. These tactics came about lengthy earlier than people existed, and will hold long after we're gone. We are observers, witnesses to a grand drama that transcends our lifestyles. Ultimately, the discoveries inspire wonder. Searching at James Webb photos, seeing galaxies billions of miles years away, spotting that we are viewing the universe as it existed in its teens. This provokes a feel of awe that transcends clinical information. It touches something deeper, a popularity of beauty and mystery that is going beyond equations and data. The universe is incomprehensibly huge. It's miles incomprehensibly old. It operates on scales of time and distance that our minds war to comprehend. But we've reached out with our instruments and our mind, peering across billions of mild years to witness the cosmos in its infancy. We've decoded the mild from historic galaxies. We have measured the loads of black holes that shaped earlier than Earth existed. We've traced the records of the universe, from the massive bang to the prevailing. That is humanity's finest fulfillment. Now not the development of towns or the invention of era, however the know-how of our region inside the cosmos. We are small, we are quick, we're insignificant, and yet we are capable of comprehending the universe itself. That paradox defines our life. We are the universe turn out to owe, and it has reminded us that notwithstanding our smallness, we've got the capacity to discover, to find out, and to marvel on the impossible vastness of the whole lot that exists. And maybe that's the most extraordinary truth of all, that the universe, vast and ancient beyond comprehension, has produced minds capable of questioning it, of looking back into the darkness and asking why. Tonight's discoveries are not the end of the story. They're only the opening lines of questions that will echo for generations yet to come. And as long as there are mysteries written in starlight, we'll keep searching for answers. So, if this made you pause, if it made you wonder, if it made the night sky feel just a little deeper, welcome to Late Night Science, where curiosity stays awake and the universe never sleeps. Until next time, keep looking up.